Hi, welcome to the Calculus 3 lecture series. And we are in the second unit to talk about the partial derivatives. So this is the lecture number 4 on the partial derivative. So in this lecture, we're going to talk about the tangent plane and the linear approximations, okay? So before we start, I need to review a little bit about the calculus 1. So what is the linear approximation? And so we already know in the calculus 1, instead of a tangent plane, we know the derivative is what we call is the tangent lines, the slope of the tangent lines, right? So we're going to do a brief review of it and then see when we kind of extend it to the R3, R4, and they still follow the same patterns here. Okay, so let's go to our worksheets here. Okay, so first things here, that's that we talk about. We need to kind of review what we did in the calculus 1 here. So let's do a brief reviews here. Then we'll be able to see how close in the R3 and in the R3 and how similar R3 and R2 is similar to here. Okay, so in here, let's take a look. This is the review in the Calc 1s, right? Okay, so here, let's see here, we have, this is my curves here. This is my functions here, right? So I say this is f of x here. And then I have a point A here, and I have a point x here. So in the Calc 1, we know the derivative is at the point A is the tangent line, the slope of the tangent lines, right? So let me try to do a slope. Let me try to do a tangent line. So this is what is the tangent lines here, right? And then from here, this is A. So this point here, this is f of A. And then this point, for here, for the x here, right? So we have, okay, so here, then this point here, we call this f of x here. Okay, so what do we talk, so like in here, right? So we said, okay, so in here, we want to use what is the linear approximation? So for a given x here, so this is the true value of the f of x, right? So I want to use these numbers here to estimate. So I want to use a point in the line to estimate. As you can see, when the x is getting closer and closer to a, this estimation for the f of x will be quite close here, right? Okay, so like in the calculus 1, we say, okay, so if you have 2 points, right? So then the slope of, if you connect the 2 points, will be a secant lines, right? So that will be the secant lines here. So if you still remember that, so we said in the calculus 1, if you connect these 2 points, it will be the slope of the secant lines, right? So let's say the slope here, okay? So the distance here, right? So the distance, this is x minus a. So the slope here will be f of what? F of x minus f of a. And then here, this is x minus a. So this is the slope for the what? Slope of the secant line, right? Slope of the secant line. So we know the slope of the secant line. So just like we said, we want to estimate this one. So the slope of the secant line can be estimated by the slope of what? Slope of the tangent lines, right? So like in here, if we say, okay, so if we say this is the linear approximation, the Lx, I'm using the line to approximate this one here. So then you can see the slope of the tangent lines. So what is the slope here? The slope of the tangent lines here will be what? Will be the Lx minus what? Minus f of a and x minus x, right? So this is the slope of what? The tangent line. So for any points in here, I call this Lx. So what is the slope of the tangent line? Is f prime a, right? So that's why from this equation, I can say the Lx minus f of a is equal to f prime a times x minus a here. So that's why I said the Lx is here, right? Is equal to the f of a and plus f prime a x minus a. So that's why I know the f of x, right? The f of x should be pretty close to the f of a plus f prime a x minus a, right? It's just basically, it's just use the slope concept, right? Okay, so now if you say, okay, so now I said, okay, let's estimate. Okay, let's estimate. Okay, so let's take a look at a simple example. Then you will be able to see how my formula going to arrive. So let's estimate here 2.04 to the squares, right? So the 2.04 to the square. So I can say the y equal to the f of x function. This real function, I can say this is x squares, right? So basically, I'm just trying to find the f of 2.04, right? So now let's see, how do I estimate? So we said, okay, so this is basically, we try to find it. So how do I use a line to estimate? We said it will be what? It will be the f of a's, right? So f of a, so I say it's 2, all right? So the 2, so this is easy, 2 to the 4. Then the x minus a, what is x minus a? Is 2.04 minus 2, right? So will be what? Point of what? 0.04 here, right? Okay, so now I can take a look at the f prime x also. The f prime x is what? It's 2x. So that's why I said the 2.04 will be very close to, what here will be close to the f prime a, right? So f prime a is 2. So it will be the f of x will be f prime a. So it will be 2. I'm sorry, the 4. X squared, so it's 4. I'm sorry, so it's 4. Okay, so let me clear that out. So this will be 4 plus f prime a. F prime a is 2 times a, right? A is what? Is 2. Then x minus a. X minus a is what? Is 0.0 what? It's 0.02 here, right? So let's see what is the answers here. So 4 times 0.04, so it will be 0.16, then plus 4, it will be 4.16, right? So this will be 4.16 here. Okay, so we said I estimate it's 4.16, right? So this is from estimation. So if you use the calculator, if you just directly put it into the f of x is 2.04, it will be 2.04 to the square. If you put it into the calculator, you will get it's 4.1616. All right, so it's very, very similar, right? So it's the approximation is very good here. And then the next thing here is we want to talk about is differential with the, the true differences here. Okay, so let's take a look here. This is still we want to see the differences between the delta y and the dy here, right? So we are going to apply this in R3s here. All right, so here, this is still in the calculus 1, and then I still have a function here, right? So this is my f of x, and then I will say here from, I choose 2 point, I will choose this is x, right? So then I will choose these ones here. I can say this is x plus dx here, all right? So this is x plus dx. X plus delta x or x plus dx is the similar here, right? So in here for the x-axis is here, right? The delta x is equal to the dx. So for this point, you can say it's x plus delta x or x plus dx. Okay, so now let's take a look at what is the y values here. So for this point here, the y value will give you what? Will give you f of x, right? And this one's here, what is this one here? Is f of x plus delta x here. Okay, all right, so now also like we have a tangent lines here, right? So let's do the tangent lines here. So the tangent line at here, let's see here. So this is my tangent lines here. Okay, so now let's make sure we understand the differences here, right? So the differences, right? So in here, the differences between this point and this point, right? So this line, this differences here, right? What is this? This is what we call this delta y, is the true differences. You know, if you plug in into your functions here, all right? So the delta y is the true differences here. It will be the f of x plus delta x minus f of x here. And we say we can use, right? So we can use the linear approximations here. This is what is our L-axis here, right? So if you just take a look, and if you want to find the differences from here to here, right? So if you just want to find these differences here, the yellow one I just highlight. Okay, so what is that differences here? This is what I called is the dy. Okay, so this is the differences I called is what is dy. That means it's the differences I used by using my tangent line. Remember here, that's why we can use here, right? The linear approximation, try to approximate the f of x. So I can use, this is will be my L-axis, right? So that the true differences is here, right? So this is the differences between these tangent lines. So it's because of these differences, so I called is what? Is dy here, right? So let's take a look. So what is dy? So we know the dy dx is equal to the f prime x, right? So the dy, it will be what? Is f prime x dx. It's kind of like mathematically, you just move over layers, right? Okay, so then I also know the dx, you know, because the x is only from the x to x plus 1, so the dx really is also equal to the f prime x times delta x here, right? So now I know, okay, so I can kind of use the dy to approximate what delta y here, right? Okay, so that's why we said, okay, the delta y is here, right? Okay, so we will say the delta y here will be equal to what? Will be equal to the f prime x and times what? Delta x here, right? Then this delta x and delta x is here, right? So it will be then times the sum of when the epsilon, the delta x is here. So that's why we said the delta y can be right as this, right? So it's equal because when they're getting closer and closer and closer, right? So it will be getting closer, right? So this is where we know the epsilon approach to 0, then as delta x approach to 0, right? So when they're getting closer and closer, this one will be the same as the delta y here. All right, so that's why we said the delta y. So if you want to say the delta y, it can be, instead of say the equal, then you will say the delta y, right, can be approximately to what? To the f prime x and dx here, or delta x here, right? Okay, so now let's take a look, right? So like in here, So this is how do we find the linear approximations, right? For the, in the calculus ones here. So now, like, so if you now, let's see how do we expand it to the calc 3s here, right? Okay, so now in here, right? So this is the, so you can say this one's here, it will be, right? So it's the f of x minus f of a is equal to f prime a x minus a, right? So now if I expand that to the z, so what I can do here, so I have a what? So I will say the z minus z0 is equal to just like f of x minus fy. So will be the partial derivative of x, right? So it's x0, y0. So this is the partial derivative. Then times what? X minus x0. Then plus, because I have a y also, right? So it's a partial derivative of x0, y0. Then this is y minus y0 here, right? So because in the R2, I only have 1. So the same ways here, let's see how do we write the delta y's, right? So in the R3, instead of delta y, what I have here, I have a delta z's, right? So the delta z, this is the true differences if you put the x plus delta x, y plus delta y, right? And then minus f of, if you give any point, f of ab, let's give any point instead of general x here. So you put in here. Okay, so here. Okay, so here, let's say that this is a plus delta x, b plus delta y. So the true delta z will just be you minus the function value. Then we know this one's here, right? What can we do here? So we can approximately, so just like in here, we can approximate by the partial derivatives, right? So this one's here, I will say I can approximately by the, what here? The f of x, the ab, then you can times delta x or dx, doesn't matter, right? Because delta x and the dx will be the same, and the fy, ab, and the dy or delta y's here. So it's the same thing because now you have 2 variables. So the delta x and the delta y is the same here, right? So that is what we talk about is a linear approximation and how to use the differential to estimate the true differences here. Okay, so that's the review of the Calc 1. So now let's take a look here. So this is what the first things we say. So instead of tangent lines here, right? So we have a tangent plane. So it's the same thing as the linear. So this is the linear approximation in the R3. So that's why we extend our equations to here, right? Just like in R2, our linear equation is what? So in R2s, right? So just from the memories here. So our is what? Is y minus y0 is equal to what? F prime, like the f prime x0 and x minus x0. So right now I have 2, I have x and y, so I can expand that to the both directions here. Okay, so now let's try to take a look this problems here. Let's say find the equation at f of xy is 4x squared and y squared. So the first, let's try to find what is f of 1, 3. So that means you just times 4 times 1 to the square plus 3. And what I have here, I have 12. So I have a point, my x0. So this is my x0, y0, right? So my x0, y0, and z0 is equal to what? 1, 3, and 12. Correct? Okay, so now let's do the partial derivative like we did before. So this is axy, and the partial derivative for y is what? Partial derivative for y is 4x squared, right? And then you plug in the partial derivative of 1, 3. So this is a times 1 times 3, so it's 24. And this is the partial derivative of fy13. So what is that one? Is 4 times 1 to the square is 4. Okay, so now I can, using these linear approximations, and write down our planes here, the tangent plane definitions here, right? So we can write this is z minus 12 is equal to 24 x minus 1 plus 4y minus 3, right? That's the plane equation. So if you kind of combine it, and you will get this is 24x plus 4y minus z is equal to 24. That's the equation for the plane we talk about in the chapter, in the previous unit, the vector and the geometry space. Okay, so now let's say, what is the equation of the tangent line? Remember, the tangent line in the R3 is like if you fix along the x-axis or along the y-axis. So let's say here, what is the tangent line? If I fix it, right, y equal to 3, so here, right? So the y equal to 3 is here. So the tangent line to the curve by the intersecting the surface about the at the y equal to 3, okay? So if when the y equal to 3 is here, so when the y equal to 3, all right, so then you will have, okay, so you will have what here? So you will have z minus 12, and it will be equal to 24x minus 1. Okay, and then also, so that's why you will have 24x minus z is equal to the 24 here. Okay, so the lines we try to find, right? So the line, because it's along the x-axis, right, and the plane is y equal to 3. Okay, so we know the f of x from the previous, we said f of x is equal to the 24, and then also z value is 12, right? So the lines here, so it will be, okay, equal to s, so we use the parametric form. So the line will be 1 plus t, because it's when the y equal to 3, that means I'm along the what? I'm along the x-axis here, right? So then the y is just equal to 3. Then the z is equal to the 12 here, right? So z equal to the 12, then plus what is the slope? What is this kind of a similar direction here? Is 24 t here. Okay, that's it. Okay, so now let's take a look at the next ones here. Next ones here, so we talk about is what is the tangent plane and what is the horizontal, right? So what is the horizontal for this one? So if you if you remember, like in the cap 1, we say, if I have for example, if I have a tangent line is horizontal, that means I'm tangents here. So what's that mean? That means f prime x has to be what? F prime x equal to 0, right? That's why we call it horizontal. So like in the R3, if I want to have a tangent plane, it's a horizontal. So it's the same. That means my partial derivative to the x has to be equal to 0, and the partial derivative to y equal to 0, right? Okay, so now let's take a look at partial derivative of x here. So this is 12x squared plus 6xy, right? And now this one has to be equal to 0. I can factor the 6x out. I have a 2x plus y equal to 0 here. So we know it will be at x equal to 0 or y equal to negative 2x, right? So that means we have to have this term equal to 0 or this term equal to 0, right? Okay, so now the same way, let's take a look at partial derivative for the f of y's here. So this is 3x squared minus 48, correct? Okay, so minus 48, so I will set equal to 0. That means 3 x squared minus 16 equal to 0. So I have x equal to 4 or x equal to -4 here. Okay, so when the x equal to 4, right? So because here y equal to the -2x, right? So y has to be equal to what? -8 here. Then when the x equal to -4, okay? Okay, so now what is the y's here? Y going to be +8 here. So I know the tangent planes here. So the tangent plane, where they're going to have a horizontal tangent plane, we know is horizontal at this point, 4 and the -8, and the -4 and the +8. Just like what we did in R1, R2s, right? So we just expanded the same ideas here. Okay, so the next ones here, we said that just like we talked before, the increment, let's mean that the true differences of the delta z's here. So the true difference of the delta z will be the f of x plus delta x, f of y plus delta y minus f of x y, right? So I know, so that we can say these ones here, we can use the what? We can use the differential to approximate, right? So it's the same idea, dz, right? So dz is here. So we can use the dz to approximate what? Delta z here, right? So it's the same like we discussed in the chapter 1. We can use delta y, dy to approximate what? Delta y's, right? This is in the R2s here. Okay, so now let's take a look. How do we do this problem? See here. Okay, so it says z is this functions, right? So is z is equal to the f of x 2x squared plus y. Find the delta z's here. Okay. Okay, so the delta z's here. Okay, so the delta z, all right. So let's take a look. How do I find? So z, okay, so z at 2, 1. Okay, so we say z at 2, 1. That means, let's put this one. So the f of x at 2, 1. Okay, so f of x at 2, 1. What I have here, I have 2 1s here. I will have like, you put it on 2, so it's 2 times 2 squared plus 1 is 9. And I can put the two differences, so this is 2.01 and what? So this is 2.0, I can put this number 2.01 and 1.03 in the functions, right? So that the function value will be 2 times 2.01 squared plus 1.03, the cubes, right? So now you will find, so this one's here, you will get these numbers here. It will be 9.1729 here. So what is my delta z? The delta z is the true differences will just be the 9.1729 minus 9, right? So from here, the function value minus 9. So you will get a delta z is 0.1729 here. Okay, so now let's take a look. How do I use approximations, right? So I know that f of x is equal to the 4x, right? So 4x, and then I said f of x at 2, 1. So you see how simple that is? This will be 8, right? Then the same ones here, the f of the y, right? So f of the y is in here, right? So the f of the y will be what? The 3y squared. Then the partial derivative of f of the y at 2, 1. What is here? So it will be, okay, so it will be 3 times 1 to the square. So this is 3 here, right? Okay, so now let's also take a look from the 2 to 2.01. So the delta x is equal to what? Delta x is 2.01 minus 2, so it's 0.01. Or, if you want, you can say delta x equal to delta dx, right? Then the same way, the dy, you can say the delta y is equal to what? Is with 1.03 minus 1, right? So it's from here, the difference here. So it's 0.03 here. Okay, so now I can figure, okay, so now here I can find the dz's here, right? So remember the dz is what here? Is f prime x dx plus fy dy's, right? So I can plug f of x is a times the pointer what? A times the pointer 01 plus 3 times the pointer 03 here. So what I have is 0.17 here. Hey, take a look here. This is the this is the delta z's, right? So this is the delta z's 17. So this is a true differences for the z. And then this is user differential is 0.17. Is that pretty close? Oh, yes, right? So I know that then the next part is the delta z minus dz. So will just be 0.1729 minus 0.17. So this is 0.0029. You see, the differences is very small, right? Okay, so then they say, hey, you know that you find it here. So let's try to use part A to estimate here. So just like we use a linear approximation, so we say, okay, so this is a 2.01, 1.03. This one will be approximately to the 2.1, right? So 2.1, then plus what? Plus the differences here, right? So plus like the f of x, 2.1, delta x plus the f of y, and the 2.1 delta y is here, right? So the 2.1, what is the 2.1? We got the 2.1s here is 9, right? So now we can say this is very close to the 9 plus, so what is, this one's here, right? So this one's here is what? It's here, right? It's dz is here. So we say it's plus 0.17. So the true value is 9.17, right? See how close it is, right? So just like we said, the differences is less than like the 2 decimals, right? So it's 0.0029. Okay, so that's what we say is the normal approximation. Okay, so now let's take a look at the number 4 here. So we said find the dz's, right? So remember the dz. What is the dz's here? It's f of x, the partial derivative of x times dx plus f of the y times the dy here. So let's try to do it. So dz is here, right? So first I need to take the derivative of x. Okay, so now this is come to here. I have a 2 function. I have x and exy here. So what I need to use? I need to use the quotient rules to do that, right? Okay, so when I use the quotient rule, so what I need to do, I need to take the derivative of x. So hold 1, so I'm holding the exy, then take the derivative of x will be just itself, plus hold the, the first one's x here, take the derivative of xy will be the self, and then don't forget what chain rules, right? So it's y, then the whole thing's here, this is dx, then plus dy, okay, dy, so this will just be the exy. Then chain rule for xy, what is here? Chain rule for xy will be what? Will be x here, right? Okay, so this is dy. So what do we have here? So the final answers here, this will be exy. We can take this out. This is 1 plus xy dx plus x squared exy dy here. Okay, so the same way, okay, so let's take a look at the same ways here. So this one's here, they say the dw's, right? So this is in the R4. So now let's try to use the same formula. So what is the dw going to be? Will be the partial derivative of x times what? Dx plus partial derivative of the y dy plus partial derivative of what? Dz fz dz's, right? So you just do the same idea from the R2, R3. Now this is R4, right? So we will apply the same idea. Okay, so now this one's here. Let's see here. This one should be pretty easy derivative. So dw, take the partial derivative of the xy, x here, so it's just be y cubed, right? So yz, both are the constant, right? So this will be dx. Then plus the dy, so the first one will be 3xy squared plus z cubed, right? So this is dy. Then plus dz, so xy is a constant, so it's 3yz squared is equal to 3yz squared, right? Then it's what? It's a dz here, right? So this is pretty simple. And the last two problems, this is really what we want to use those estimate for, right? So we said, okay, try to estimate the value 3.02 to the square, 0.99 to the cube. Imagine if you don't have a calculator, they probably take a while to really calculate that. Okay, so now let's use the idea of the estimation. So I will say z is a function. All right, so this function's here. What function I can call this one? I say is x squared to the y to the -3. Okay, so now I want to basically what I'm an estimate. I'm an estimate of f of what x will be what 3.02, right? And the y is what 0.99. All right. Okay, so now we can say, okay, so in the here, so first one here, so that means I'm going to use the point. So I'm going to use the point AB is equal to what? 3 and 1, right? So first things I'm going to put, what is my point value? 3 and 1. So that will be 8 over -1, right? 3 and 1, no, 3 to the square, so it's -9. So y to the, y is the positive, and so 3 and 1, so here it's cube, so it's 9, all right? So F3 is 9. Okay, so now we're going to use the, the linear approximation to estimate, all right? So we're going to use the delta z, try to dz to estimate delta z is here. Okay, so here the partial derivative of x. So what is partial derivative of x? Is 2xy -3. Okay, so plugged in the 0.31, right? So this will be 2 times 3 is 6, right? Okay, so then the partial derivative of y, see here, this will be -3 x squared y to the -4. Then plug in my 0.31 is equal to what? 31 is 927. So it will be what? -27. Very good. Okay, so now let's take a look at what is my dx or delta x here is from 3.02 to 3, right? So it's 0.02, correct? Okay, then what is my dy or delta y here? It will be from 0.99 and 1. So the difference is here. This will be -0.01 here. Okay, so now I know, okay? So now the dz, so let's try it one more time. So it's f of x dx plus f of y dy. So this will be f of x is 6 times 0.02 plus negative 27 times negative 0.01. All right, so the dz is equal to the point of what? 0.39. Right? So now I know the f of the 3.02 and the 0.99 will be approximately to the f of the 3.1 plus what? Plus the delta z's, right? And the delta z can be, so I should say this, be careful about my notations here. So this will be equal to that. Then so this will be very close to f of the 3.1 plus dz, because the delta z can be approximated by the dz. So what is the dz we just get here? 9, right? So it's 9 plus, okay? So the 9 plus 0.39, so it's 9.39. Okay, so this is our estimate, right? 9.39. If you put the whole number into the calculator, okay, so if you use the calculator, you will get this number is 9.3996. As you see, still it's pretty good. It's close, the estimated value close to like the 2 decimal point. That's really, very good, okay? So the number 7, this is a part of the problems here, and it's very useful problem in the real life here, because a lot of time when we try to calculate something or measuring something, the gauge you use have a mark, you have arrows there. So what means the arrows there? That means that is our delta x dx here, right? So then, you know, if you try to use a ruler to measure some shape, then if your ruler have an arrow, then when you calculate the area going to have an arrow. See here. So let's take a look how is this one work. So let's say a circular pool is 7 meters in diameter and 3 meters deep. But if the measurements are accurate to within the 0.05, then use differential to estimate the area and calculate the volume of the pool. Okay, so I know, okay, so first here, so volume, this is V equal to pi r square and the H, right? So R is 3.5 and the H is equal to what? It's 3, right? So H is the height here. But because when I'm measuring it, my measurements has an arrow, you know, within the 0.5 meters. So what's that mean? That means whenever I measure the R, my delta R could be what? Could be plus or minus 3.5 plus or minus 0.05, because sometimes I will read a little more, sometimes I will read a little less, right? So the same way, because I'm using the same measurements tool, then my delta H here will also is a point of what? Will be 0.05 here. So because sometimes I'm going to read a little bit more, sometimes I'm going to read a little bit less here, right? Okay, so my true, if I don't have, right, if I don't have the measurement error, so my true volume should be what? It's pi r squared, right? R is 3.5 squared times 3, all right? So so it's a pi r squared, so it will be, if you put it into the, so this is my true, so this will be 115 point, you put the pi as 3.14, 45353, 45353 meter to the cube. Because of this, okay, so they want me to estimate what is the error, right? What is the error when I calculate the volume? So this is the true volumes, right? So if I don't have any error when I measure it, but when I do have the error, so let's say here dv, right? Let's take a look at I have two variables, both can have an error. It's radius and the height, right? So, okay. So let's take a look at the radius. So this will be 2 pi r h. Then is dr, right? Then plus, right? So then to the height, right? So my height here is what is pi r square, and the dh is here, right? So basically, if you take a look at what is this one, this is a partial derivative. So I will say partial derivative for x, and this is the partial derivative for the height here. All right, and so I know these ones here, those offness, right, going to have a measurement errors here. So the dv, right, so dv going to be estimated by the 2 pi r h and delta r plus pi r squared, the delta h is here. So now we're going to be close to 2 pi. So what is r is 3.05, h is 3. Then the arrow for the r is 0.05 plus pi r square. So it's the 3.5 square, right, times the delta h is 0.05 here. So if you calculate that, so the value will be 5.22 meter cube here. So we calculated, so the dV is going to be the 5.22 meter to the cube. So that means, right, so the true volumes here, right, will be here like 115.5 meter cube. Because of your measurement error, so you will calculate the volume, you know, could vary from 120 and from 110 to the 120 because you do have the measurement error. This is, of course, we said that the measurement error within, so that's the maximum error I can have. That means your true volume you calculate could from the 110 to the 120 ranges here, right? Like I said, the problem number 3, this type of problem is very, very commonly used problem in the industry because a lot of time when they do something, they always associate with the error in the input variables here, right? If your input variables have a certain error, then your output variable going to have a certain errors here, right? So that's how do we use the, you know, easily we use the differential and try to estimate the real errors here, the increment for the differences between the function. All right, that's it. And it's very interesting, the sections, and it's a very useful sections here. And this section connect very closely to your calculus 1 linear approximations. Okay, so it's the same idea. You can easily expand this idea to the R3, R4, and R5. Okay, that's it. Nice talk to you, and you have a good day. Okay, bye-bye.